My dear students, let me welcome you all to a new edition of physics. In this edition, we'll start chapter 4, AC circuits. Also, in this edition, we'll learn about the hot wire ammeter, its structure, its idea, its mode of work. Also, we'll be able to make a comparison between hot wire ammeter and moving coil galvanometer. So let's get started. AC circuits. First of all, we'll try to define alternating current. What's meant by alternating current? Okay, thank you very much. It is an electric current which varies in strength and periodically reverses its direction. This was about the definition of the alternating current, and it is shown in front of you. It is represented by a sine wave. Okay. And what about the frequency of the alternating current? Yes, it is the number of complete oscillations, complete cycles performed, made by the current in 1 second. So let me say it again. What about the frequency of the alternating current? It is the number of the complete cycles made by the current in 1 second. And now we'll talk about the advantages of the AC current over the DC current. Advantages of alternating current over direct current. First of all, AC current can be generated at high voltage. So it can be transmitted efficiently through power lines over long distances without much loss. So I'm going to say it again. Alternating current can be generated at high voltage. When the voltage is stepped up, current is stepped down. In this way, we decrease the loss in power in form of heat. AC current can be generated at high voltages, so it can be transmitted efficiently through power lines, power cables, over long distances without much loss. AC current can be stepped up or down as needed by using electric transformers. So if you want to step up the current or step it down, it's all easy by using transformers. Step-up transformers or step-down transformers. AC current can be converted into DC current, can be rectified. Okay? Both AC and DC currents have thermal effect when passing through a resistor. This is very important because we'll depend on this fact when making a device that measures AC current and DC current, hot wire ammeter. So once again, both AC and DC currents have thermal effect when passing through a resistor. The power of the AC current is not consumed in coils and capacitors. Power of the AC current is not consumed in coils and capacitors. That's to say, no electric power is dissipated in form of heat in coils and capacitors. And now, talking about hot wire ammeter. Hot wire ammeter is the device used for measuring mainly AC, and also it can be used to measure DC currents. Okay? Simply because it is based on thermal effect. Okay, so talking about hot wire ammeter. First of all, construction and operation of the hot wire ammeter. In front of you, we've got the main components. First of all, we've got thin wire or resistance wire, and it is made of platinum iridium. Okay. Also, we've got, yes, silk thread. Okay, what about the silk thread? One end of the thread is tied to the middle of the resistance wire, and the other end is wound around a pulley and fastened to a spring, as shown in front of you. And also we've got, yes, a pointer that moves on a scale. Your attention, please. The scale is not uniform. It's not equally spaced. It is shown in front of you. And also we've got something like a shunt to increase the range of the device. Okay, this was about the structure of the hot wire ammeter, and this is very important, and you should learn how to draw it. And now, talking about uses of the device. It can be used for measuring the effective value of the AC currents, and it can be used for measuring direct currents. So it measures effective value of the AC currents, and it measures direct currents. And what about the operation of the device? Let me remind you something. It is based on thermal effect of the current. And now talking about operation of the device, its mode of work. Okay, when the current to be measured is sent into the device, is passed through the device, the platinum iridium warms up. An amount of heat is generated and sags. Okay, it expands, so it sags. The sag is taken up by the silk thread, which is held taut by the spring. The spring rotates, and so does the pointer. So the sag is taken up by the silk thread, which is held taut by the spring. Okay, and the pulley rotates, and attached to the pulley, the pointer. So when it rotates, when it moves, the pointer rotates and moves. The deflection of the pointer, this is very important, is proportional to the average rate at which the heat is developed. It is therefore proportional to the average value of the square of the alternating current. Heat is given from the expression I squared times R. So it is proportional to the average value of the square of the alternating current. And the scale is a square law 1, so it's not uniform. Theta angle of deflection is not proportional to I. It is proportional to I squared. That is why the scale is not equally divided. And now we've got something very important to mention. We've got important hints. First of all, a moving coil galvanometer cannot be used to measure AC current. Now I'm talking about a moving coil galvanometer. Okay, we cannot use it to measure AC. Why? Yes, if an AC current is passed through a moving coil galvanometer, the pointer does not move. Why? We want to explain this. Don't ever forget that the device, the galvanometer, is based on magnetic effect, which depends on the direction of the current. Okay, the coil is urged clockwise and anti-clockwise because the current reverses direction at the frequency of the current and does not move at all. So the coil will be pushed to move in a direction and pushed to move in the opposite direction with high frequency, but it cannot do this, it cannot perform this, so it just records the average, which is 0. Once again, the coil is urged clockwise and anti-clockwise at the frequency of the current and does not move at all. The coil cannot oscillate with the same frequency of the current, so it just records the average value of the alternating current. And of course, you remember the average value of the alternating current in one cycle is 0. Another important thing to bear in your mind, hot wire ammeter is calibrated by connecting it in series to a moving coil galvanometer. Also, when current is passed through the resistance wire, the wire warms up till it reaches a temperature. Okay? So at the very beginning, it warms up till it reaches a temperature at which it loses heat at a rate equal to the rate at which heat is developed. So, yes, it stops further expansion. Okay? At which, at this temperature, it loses heat at a rate equal to the rate at which heat is developed in the wire. And now talking about disadvantages of the hot wire emitter. What about disadvantages of the hot wire emitter? As a matter of fact, one major defect here is the pointer deflection is so slow when the current is passed through it. When the current required to be measured is sent into the device takes time till the pointer comes to rest and measures. Okay? This is the first disadvantage. The pointer deflection is so slow when the current is passed through it. Also, the pointer returns slowly to zero scale when the device is disconnected. Atmospheric temperature affects the expansion of the resistance of the wire. Okay, atmospheric temperature means temperature of the surroundings. Okay, affects the expansion of the resistance wire, and this may cause a zero error. To eliminate this effect, to eliminate this error, the resistance wire, and this is very important thing, the resistance wire, the platinum iridium wire is mounted, is placed on a plate made of platinum iridium or any metal that have the same, any metal having the same expansivity. Thus, the wire and the plate expand equally, keeping the wire with the same tension. Okay. To answer some questions on the hot wire emitter. First of all, give reason for. In the hot wire emitter, a wire of platinum iridium is used. Why platinum iridium in particular? Okay, the platinum iridium alloy has high coefficient of expansion. It has high expansivity. So it shows considerable expansion when a current passes through it. Another give reason, the scale of the hot wire emitter is not uniform. This is the most important piece of information about the hot wire emitter. Scale of the hot wire emitter is not uniform. Why? The function of the hot wire emitter depends on thermal effect of the current. It depends on the thermal effect of the electric current. Thermal effect of the electric current is determined from the expression from the relation I squared R. So the deflection of the pointer theta is directly proportional to the average value of the square of the alternating current. Theta is proportional to I squared, not proportional to I itself. That's why the scale is not uniform. Another give reason, the hot wire emitter can measure both AC current and DC current. Okay. As a matter of fact, the function of the hot wire emitter depends on the thermal effect of the electric current. And both AC current and DC current have thermal effect, so they can be measured by the hot wire emitter. Another give reason, the hot wire emitter is provided with an adjustment screw to adjust the pointer to 0 scale. Okay, why? The resistance wire is affected by changes of the temperature of the surroundings. It is affected by changes of the atmospheric temperature. So its pointer moves away from the 0 scale, and hence it requires adjustment before using it. Another give reason, the resistance wire of the device of the hot wire emitter is stretched over a plate made of a material that has the same coefficient of expansion as the wire. This to eliminate the effect of the atmospheric temperature of the surroundings. In this way, the wire is kept taut as the plate will expand by the same amount as the wire. And now we'll make a comparison between moving coil, galvanometer, and hot wire emitter. First point of difference is the idea of each. Moving coil galvanometer is based on magnetic effect, but hot wire emitter based on thermal effect. So, moving coil galvanometer is based on the magnetic effect of the electric current. Also, you can say it is based on magnetic torque, but hot wire emitter is based on thermal effect of the electric current. Moving coil galvanometer measures only DC currents. It only measures DC currents. Hot wire emitter measures effective value of AC current, and it measures DC currents. The scale of the moving coil is uniform. Angle of deflection theta is proportional to the current itself, but the scale of the hot wire is not uniform. Theta is proportional to I squared. The pointer of the device, when using the moving coil galvanometer to measure a current, the pointer comes to rest. Pointer of the moving coil stops moving when the electromagnetic couple is balanced by the mechanical couple produced by hair coils. And pointer of the hot wire emitter stops when the resistance wire reaches a temperature at which the heat produced in the wire due to the flow of the current equals the heat lost by convection. Moving coil galvanometer has high sensitivity, but hot wire emitter has much lower sensitivity. Talking about disadvantages of each one of them, disadvantages of the moving coil galvanometer. As time elapses, the hair coils, hair springs become inactive. They slacken away and the magnet loses some of its strength, so the device requires recalibration from time to time. Also, it measures DC only. Talking about disadvantages of the hot wire emitter, its sensitivity is small. It is affected by atmospheric temperature. Also, pointer takes long time to measure the current required to be measured, and it takes longer time to return to zero when the current is disconnected. And now talking about AC circuits. The first circuit is shown in front of you. It is AC current in a non-inductive ohmic resistance. Okay, non-inductive means we don't have any self-induction. This happens when the coil is doubly wound. Okay. So we've got a source. This circuit, of course, is powered by AC current. Okay, powered by a dynamo. Okay, so when the circuit is closed, the instantaneous potential difference across the resistor is given from the relation. Of course, you remember it. Instantaneous EMF denoted by V equals maximum EMF, or V maximum sine omega t. This is the first equation. Okay, and let me remind you with omega t is theta, which is the phase angle. Dividing both sides of the last equation by R, we'll obtain the following equation. V over R, instantaneous voltage, equals V maximum over R sine omega t. Voltage divided by resistance is current, so I instantaneous equals I maximum sine omega t. When we compare these two equations, V instantaneous equals V maximum sine omega t, I is equal to I maximum sine omega t, it is quite clear, yes, that the voltage and current are in phase. So phase angle between them is 0. Okay. It is shown in front of you. Okay. And now talking about the second circuit, AC in a pure inductance. Pure inductance is denoted by L. It is inductive coil of 0 ohmic resistance. Okay, it is shown in front of you. We'll apply Ohm's law of closed circuit here. So if we apply Ohm's law of a closed circuit to the current, to obtain the current flowing in the circuit, we'll obtain the following relation. Current equals, we've got two voltages. Voltage of the supply and EMF, yes, induced by self-induction, so V minus L di by dt over R. And we are talking about pure inductance. Pure means resistance equals 0. So we can say IR is equal to V minus L di by dt. And as I said, R is 0 since it is pure. So we can say V is equal to L di by dt. Okay. So since instantaneous current is equal to I maximum sine omega t, the voltage is equal to L di by dt, substituting for the current. So d between two brackets I maximum sine omega t. So V will be equal to omega L I maximum cosine omega t. The last expression can be written as follows. Cosine will be replaced by sine, and we'll add pi over 2. So V is equal to, yes, L I maximum omega sine between two brackets omega t plus pi over 2. So V equals V maximum sine omega t plus pi over 2. This is the first equation. This is the equation that gives the voltage. And what about the current? I is equal to I maximum sine omega t. If we compare the two angles here, in the first equation we've got sine omega t plus pi over 2. In the second, sine omega 2 only. Okay? So the voltage, it is quite clear from equation 1 and 2, it is clear that the current in a pure inductance lags pi over 2 behind the voltage. That is to say, the voltage leads the current by, yes, 90. It means that the current passes its maxima a quarter cycle later than the voltage. Okay, when we say current lags behind, it means that the current passes its maxima a quarter cycle later than the voltage. It is shown in front of you. Okay. And now we'll try to obtain the quantity that represents the opposition to the flow of the current. Okay? Voltage leads on the current by 90. So we want an expression that gives the opposition. First of all, V maximum is equal to Li maximum omega. Okay, so we can say V maximum over I maximum equals L omega. Voltage when divided by current gives, yes, what represents resistance. So it is equal to XL, inductive reactance. Okay, so inductive reactance XL is equal to omega L, and omega is equal to 2 pi F. So XL is equal to 2 pi FL. In this way, unit of reactance, it is just like resistance. It is some sort of opposition. It is measured in ohm, frequency in hertz, and inductance in Henry. And inductive reactance is defined. If we want to give it a definition, it is defined as the opposition that a pure inductance offers to the passage of the alternating current due to its self-inductance. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.